So today we move on from Newton's laws, but not really, because everything that we do in the rest of this course builds up on Newton's laws. So we try to move on, but we cannot. Okay. So anyway, so you have Newton's second law, remember, is the central equation of dynamics, F is equal to ma. And until now, by and large, we have applied F is equal to ma to study the problem of why objects move. We have basically answered that an object state of motion changes when there is a net force acting on an object. And we have looked at the different types of forces that you commonly encounter in the macroscopic world. And until now, there has been a big restriction regarding the forces that I have dealt with, by and large. The kind of problems that I dealt with until now, they involve forces which are constant. Okay, so for example, I studied the problem of an object falling near the surface of the earth. As the object falls down, it encounters a constant force mg downwards. I considered a spring being extended but the extension was fixed. So essentially the spring force, whatever spring force was acting, it was the same in size. There was no oscillatory behavior, that the spring wasn't oscillating here and there, so that the extension was not changing. If the extension was changing, then of course you would be dealing with a problem in which the force was changing. But we weren't doing that. Okay, so you are essentially doing problems in which the forces by and large are constant. Okay. Now the next complication comes in when you want to deal with forces that are changing. When you talk about forces that are changing with time, the first question that comes up immediately is, well, how exactly are they changing? I'm not talking about what's the function that describes how the force is changing, but essentially a very basic question, that if you are given how the force is changing, are you given how the force is changing with respect to position, or are you given how the force is changing with respect to time? So for example, if you are pushing a box, I give you, and you vary the push. You vary the force by which you are pushing this box. You could specify this variation in terms of time. You could say, for example, at t is equal to 0, my push is 5 newtons. At t is equal to 5 seconds, the push is 15 newtons. And when t is equal to 100 seconds, the push is 100 newtons, and so on and so forth. Okay? That's specifying the force as a function of time. It is a changing force, but I've described in terms of exactly how is it changing in terms of time. Alternatively, I could describe the changing force in terms of position. So I could say when the box is at x is equal to 0, the force that I'm applying is 5 newtons. When the box is at x is equal to 1 meters, the force that I'm applying is 50 newtons. When the box is at x is equal to 50 meters, the force that I'm applying is 500 newtons, whatever. Okay, so I'm describing instead the variation of the force as a function of position instead. Okay, and the two big developments that take place in our formalism is essentially to look at these two dependencies. If you look at the dependence on force with respect to time, you land up on the idea of momentum, linear momentum. If you look at the dependence of force with respect to position, you end up with the idea of work and kinetic energy and potential energy and conservation of energy. That's where it all starts from, that you look at the dependence of force on position. Okay. Roughly speaking, okay, well, it actually is that, but giving you the broad overview, Newton's second law says that the net force acting on the object is related to the mass of the object times the derivative of the velocity vector. This equation involves a derivative. And there's a close mathematical relationship between the language of derivatives and the language of sums or integrals. If you choose to write down the same equation, since you know that in some sense derivatives and integrals are related to each other, if you choose to write down the same equation using the language of integrals instead, you end up with, well, either linear momentum or you end up with work and energy and kinetic energy and potential energy. If you choose to integrate the force with respect to position, you end up with the work done, the kinetic energy, the potential energy, the conservation of energy. If you choose to integrate force with respect to time, you end up with essentially linear momentum. Okay, so basically our next big developments will essentially use the fact that derivatives and integrals are very closely related to each other. If you can write down an equation that talks about derivatives, you can write the cousin equation that talks instead about integrals. Okay, the first cousin equation, so to speak, okay, right, is the following. I'll just write it down, and the objective of today's lecture is to actually understand what in the world does this horrible looking equation mean. Okay, so that's what we have to do. Today my objective is to teach you some language. Okay, so F, except that this is the language of mathematics. Okay, F dot ds from A to B equals the change in the kinetic energy. That's basically where we are going to end up with by the end of today's lecture. This is something called the Work-Kinetic Energy Theorem, for the obvious reason that the left-hand side is defined as a physical quantity called the work. So the work is the integral of force essentially over distance. This ds is a small displacement vector. What exactly do I mean by that? Well, that will become clear in due course. And the right hand side is the change. That's what this delta means. This is not triangle KE. This is delta kinetic energy, the change in kinetic energy. In particular, this is equal to, the change in kinetic energy is equal to half times the mass of the object times the velocity at B squared minus half times m times the velocity at A squared. Okay, what do I mean by the square of a vector? I just mean the magnitude of the vector squared. Okay, in other words, you'll see that very soon. Okay, so that's basically where I'm going towards. Okay, and unfortunately for you, as we go on, some of these ideas become quite abstract, because we can imagine what a force is. In some sense, a force is always a push or a pull, physically speaking, but you cannot really imagine what work is. All I can really give you is a mathematical definition of this quantity called work. You cannot really have some physical intuition for exactly what work is, except that this does give you a slight amount of physical intuition, because if the work done on something is positive, that means that that object is speeding up. If the work done is negative, that means that this object is slowing down, because when the object is speeding up, the right hand side will be positive. When the object is slowing down, the right hand side is negative. Okay, in physics, as in all science, you always define change as final minus initial. Okay, so that language issue goes away. Change in kinetic energy is always the final kinetic energy minus the initial kinetic energy. Do not confuse this change with initial minus final. Linguistically, that's fine, but when you're doing science, change is always implicitly defined as final minus initial. Okay, okay, so let's start. Why are we even bothering to do this? That, of course, is the first question that they need to answer. That otherwise it's pointless. Why am I even bothering to set up this abstract mathematical formalism? Why am I even doing that? Okay, other than, of course, that you need to learn this to get enough marks so that you can do machine learning in the future. Other than that, the biggest reason being physically is that this formalism allows you to attack many problems and solve them in 2 lines, which would have taken you many lines if you just use Newton's second law directly. When I say using the Newton's second law directly, I'm meaning this, of course. Newton's second law written down in the language of derivatives. This is actually nothing other than Newton's second law written down in the language of integrals rather than derivatives. Okay, that's all it is. But the integrals with respect to position rather than time. When you integrate force with respect to time, you end up with something called linear momentum. That we will do soon enough, okay? Right, so let's start. Okay, why am I even doing this? Just to illustrate you a problem that you can do very simply with this approach. Say you have the earth if you drop an object, if you release an object far away from the surface of the earth. So you release an object from rest very far away from the surface of the earth. Just for simplicity, I'm releasing it from rest. You don't need to release it from rest, you can actually throw it. Okay. And then the problem that I give you is that what's the speed of the object when this object hits the surface of the earth? Well, essentially you cannot use that because the force keeps on changing. When the force keeps on changing, because the force over here, the force that this object is experiencing over here is different from the force that the object is experiencing over here. And therefore, the acceleration that the object experiences keeps on changing. Therefore, you cannot simply say that v square is equal to 2as. I'm just writing 2as because u is 0 for my case because I release it from rest. But I know you won't be able to resist this temptation. You will still be writing v square is equal to 2as. In this case, it does not apply because the acceleration is not constant. Right? And you only know the force that is acting on the object not as a function of time. You know the force acting on the object as a function of position. If I say that the object is over here, you know the force acting on the object. That's the gravitational force between the earth and this object. This object is very far away, so I have to use Newton's law of gravitation to compute the force. I cannot just approximate the force as mg pointing downwards. When the object gets closer, the force increases. The acceleration that the object experiences increases. So the force keeps on changing, the acceleration keeps on changing. How exactly does the acceleration change? It's not easy to figure out directly. But with this language, I can solve this problem in 2 lines. And there are many other problems, okay? You don't need to do something that exotic. You take a block, you attach it to a spring. And then you pull the spring and let the block go. The spring force keeps on changing with the position of the block. As the spring comes back to its natural position, to its natural length, the force that the spring exerts on the block is 0. When it overshoots, when the block overshoots, it goes to the other side, then again the spring is exerting a force on the block, but now it's exerting a force to the right. Initially, when the spring was stretched, the spring was exerting a force on the block to the left. Okay? So the force keeps on changing. This can be quite subtle, okay, as well. So if you have, for example, a hemispherical bowl, you take a marble or a tiny ball and you put it at the rim of this bowl and you let it go. The force, when I say the force, I mean the net force acting on this marble, keeps on changing with the position of this marble. Because essentially when the marble is over here, you have essentially a force mg downwards. This angle is theta, so you have mg cos theta over here as this component. You have a normal force acting on the marble, and then you have mg sin theta over here. Of course, theta changes with the position of the marble. When the marble is over here at the very bottom, theta is 0? Okay. When theta is over here, the marble is 0. Yes, okay, over here. Okay, anyway. When the marble is over here, what is theta? 90 degrees. Okay, so theta keeps on changing, and therefore the net force keeps on changing. The net force in the tangential direction keeps on changing. By the way, what's the net force in this direction? No, 0 nahi hai. It's moving in a circle with this point, with the center of the bowl as the center of the circular motion. So you will have n minus mg cos theta equals mv square over r. Okay, the net force towards the center will be providing the centripetal acceleration essentially, the acceleration that is required to change the direction of the velocity vector. Okay, so in this case, of course, आप naively कहोगे भाई sir mg तो as the marble moves, mg remains the same. Sure, but the component of mg keeps on changing. The net force acting on the marble keeps on changing. Okay, right. So you have many different situations in which. In this case, the position was being specified by theta. In this case, the position was being specified by x, the horizontal position of the block. In this case, the position was being specified by maybe y, the vertical position of this object, and so on and so forth. Okay, huh? No, because the speed would keep on changing. You have to work it out, okay, right? We will work it out soon enough. Okay. Okay. So hopefully that's enough motivation for you to go on, that you have very commonly to encounter problems in which the force that is changing as a function of position. Okay. And then we need to learn some techniques, some simple techniques to apply that will allow us to attack such problems. And it goes much beyond that, because once you learn these techniques, you learn the idea of work and energy and so on. And energy, of course, is an idea, is a physical idea that basically occurs in every field, even in computer science. Okay. Anyway, so let's start. Okay, so let's start with the simplest example. Essentially, my idea always is that I want to cook some quantity which involves the force and the distance. I want to cook up a mathematical quantity that involves the force and the distance, and this mathematical quantity should give me the change in this quantity. It should give me essentially the change in half mv square minus half mu square, if you want to put it that way. Okay. So you start from the simplest case. The idea is that essentially this prescription, that's the most general prescription of calculating this abstract quantity, that is equal to the change in kinetic energy. This prescription, you will see as we go on and go on and go on, we'll make it more and more refined. Okay, so right now I'm dealing with the simplest case. You have an object near the surface of the earth and you release it from rest. The only force acting on the object is mg. I'm ignoring a resistance. The object falls through a distance s. Okay, so over here, I prefer to use s for distances because I don't like r to use r over here for distances. Until now, I'll be using r for the position vector. So then you would say that a small change in the position vector would naturally be denoted as dr. The only problem is that r very soon is going to be used for many different other things as well. The radius being one of them, the center of mass being another. So I really don't want to get a zoo of these r's. So that's why I prefer to use s for displacement, okay, or position. Okay, over here it falls through a height s. You can use r if you want. That's fine with me as long as you keep it clear in your head. Okay. Anyway, so if I make the curious observation that I multiply the force acting on the object, I multiply that with the distance. Yeah. If I multiply the total force acting on the object with the distance that the object has traveled, okay, this is equal to, this is a constant force. So I know that v square equals, in general, u square plus 2as in this case. So therefore, I can write s as v square minus u square divided by 2a, and I'll just have that this thing is v square minus u square divided by 2a. And this equals, yeah, in this case my expression is equal to what? G, yes, thank you, okay. This G cancels this G and you're left with half m v square minus half m u square. Oh, so that's nice. If I ask you that I dropped an object from 10 meters high up, I ask you what's the speed of the object when it hits the ground, you don't need to draw any force diagram, free body diagrams, you don't need to draw any, you don't need to think much. All you need to do is to multiply the weight of the object, multiply that with the distance that the object has fallen. If you release the object from rest, that thing will just be equal to half mv square. So m and m cancels and you straight away have your answer. That is, of course, what you do when you apply conservation of energy in high school. The initial potential energy, the initial gravitational potential energy gets converted to kinetic energy. But that everything over there, kinetic energy, potential energy and so on, follows from what we are doing, okay. So right now I'm just playing around, okay. So you just take the weight acting on the object, multiply that with the distance, and that gives you a very neat, nifty way of figuring out the velocity of the object when it's about to hit the ground. Okay. Let's do another example. maybe the same trick applies in a different scenario. You have a box, you're pushing the box with a constant force F. There's no friction, there is the weight of the box, there's the normal force. There's no vertical acceleration, so the normal force in this case equals the weight. The net force acting on the object is simply the force that you are applying. If I multiply this force that you are applying, the man force or the woman force, one of your favorites, okay, if you multiply this with S, the distance that the box moves, what do you get? You can write this alternatively as ma times S, where m is the mass of the box and a is the acceleration of the box. And this is equal to, once again, ma times v square minus u square divided by 2a. This is basically the same thing as before, except that instead of the acceleration of free fall, now you have acceleration a. A and a cancels, and I'm again left with half m v square minus half m u square. So if I say that you apply on this box of mass 10 kg, you apply a force of 20 newtons, constant. Over here the force is constant, and the box travels a distance of 10 meters. What's the final velocity of the box? You don't need to essentially first figure out the acceleration of the box, and then you have to figure out, well, how long was the force being applied, and then you have to figure out, you then use v is equal to u plus at. You can directly do it with this. Just multiply the force by the distance, and that gives you the change in this quantity half mv square. ये constant force के लिए अभी इसको मैं generalize करना है. Of course, right now it's pretty useless in the sense that I could already solve this problem in a pretty straightforward way. हाँ, अभी तक constant ही है, yes, okay. This because this is only for constant acceleration, because I can only use this for constant acceleration, okay. The idea is, of course, to take this as a starting point, take this as a seed and build up on top of this, okay. Relax one assumption at any one time. Okay, suppose now that I push down on the box like that, so that the push that I'm applying makes an angle phi with the horizontal, or theta with the horizontal, whatever you want to call it. I called it phi, so let's stick to that, okay. Of course, इधर आप कहोगे सर ये तो man force बन गई है, ये perpendicular ही नहीं है box के. You said कि जो pushing force होती है वो perpendicular होती है, ये क्या, ये तो man force है, ये तो नहीं normal force है. If it was the normal force, it would have been perpendicular to this surface. तो फिर क्या? In actual fact, if you're pushing the box like that, आपने एक हाथ ऊपर पकड़ा होगा, एक इधर से पकड़ा होगा. This is the sum of those two forces. There's one force that you're applying like that. There's another force that you're applying like this. Both of these forces are perpendicular to the surfaces involved. The force that you're applying like that is perpendicular to this surface. The force that you're applying like this is perpendicular to this surface. This is the sum of those two forces that you are applying. तो ये दो contact forces का sum है, इसलिए आपको जो है वो perpendicular नहीं नजर आ रहा. Yes.
किसी कंडीशन में हम डायगोनल फोर्स नहीं लगा सकते?
लगा के देखो. बड़ी जल्दी आप उसी वक्त नहीं, अगर contact force है फिर तो नहीं आप लगा सकते. Contact force has to be diagonal, has to be perpendicular. नहीं, आपकी diagonal total हो सकती है, then you have to apply two different contact forces. वो पे आपकी नीडल बहुत चल रही, आप एसेंशियली हॉरिजॉन्टली लगा रहे होगे. करके देखना ओके. राइट, वो नीडल की डिफरेंट साइड से नॉर्मल फोर्स लग रही होगी ना फिर. ओके, नॉट द मेन पॉइंट. ओके, ये बाद में बहस कर लेंगे कि आप चॉक बॉक्सेस को कैसे पुश कर दो. ओके, द एसेंशियल पॉइंट बीइंग दैट यू आर अप्लाइंग अ फोर्स एट एन एंगल, ये बाद में डिस्कस कर लेते. ओके, यू आर अप्लाइंग अ फोर्स एट एन एंगल विद रिस्पेक्ट टू द हॉरिजॉन्टल. ओके, and now I do the same thing. I take the magnitude of this force, multiply with the distance that the box travels. Do I still get this thing? Q. Because there's only the component, the horizontal component of the force, only that is going to cause the horizontal acceleration. So F cos phi times S will be equal to this. Okay, in other words, what you will have is that MA equals F cos phi. And therefore, if I do Fs, this will be equal to किसके बराबर? Ma over cos phi. And then of course I have Ma, this was S, and then I have Fs cos phi will be equal to that. अब ठीक है. So I redefine this quantity that I'm talking about, force multiplied by distance, to instead be force multiplied by distance multiplied by the cosine of the angle between what? Between the force vector and the displacement vector of the box. That's what phi is. या ऐसे क्योंकि वो वर्टिकली तो मूव ही नहीं कर रहा ना बॉक्स. नहीं, वो नीचे की तरफ पुश कर रहा ना, ग्राउंड इतना स्ट्रांग है कि उसको नीचे नहीं गिरने दे रहा. नहीं, हॉरिजॉन्टल सरफेस पे डब्बा है, उसको मैं नीचे की तरफ यूं पुश कर रहा हूँ स्ट्रेट. नहीं, एक आपकी एक ही बनेगी, उस तरफ आते हैं. अभी तो मैं सिंपल 1D का रहा हूँ. Okay, is this fine? So the idea again, remember, is always that you are trying to update your prescription of calculating this mathematical quantity so that you get the change in essentially half mv square. And now you see that, okay, in a more general situation, you don't just have to multiply force with the distance, you have to multiply the force with the distance and then multiply that with the cosine of the angle between these two vectors. So then since people were lazy, they came up with a notation for this recipe. In actual fact, they said, भाई इस recipe को इस्तेमाल करने के लिए, this quantity, to actually use this, you are essentially using two vectors. One vector being the force vector, the other vector being the displacement vector of the box. And I'm combining these two vectors to give me a number which is equal to the magnitude of the force vector multiplied by the magnitude of the displacement vector multiplied by the cosine of the angle between the two vectors. Okay? So what they said is, okay, let's write a shorthand for that. Given two vectors f and s, you can define this as f dot s. जो आपका डॉट प्रोडक्ट है वो essentially वर्क और एनर्जी से ही आया था. There's a reason why mathematicians did not define this as fs sin phi. They did not define it as fs tangent phi. They did not define it as fs secant phi. The simple reason being that this is just shorthand for the work done. This is essentially the first basic application of the dot product. This is known as the dot product of two vectors, is in calculating the work done. And the work done, as I've shown you, very naturally contains this factor of cosine phi rather than sin phi or tangent phi or secant phi. Okay, you can define things in many different ways mathematically speaking. Whether those definitions lead to something useful or not, that's a separate matter, provided you did the mathematics correctly, of course. Okay? Right. So you can generalize this. Given two vectors A and B, the dot product or the scalar product of these two vectors is defined as the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between the two vectors. There's a confusion over here when I talk about the angle between the two vectors. If I have one vector like that and I have another vector like that, the angle between them, you will say, well, it's obviously this. Sure. But what about this? This is your first vector and then this is your second vector. Which angle do I take? Is this the angle between the two vectors? Yeah. So if you are encountering such a situation, when you're talking about the angle between two vectors, make sure that both vectors are either diverging from a common point or converging towards a common point. And then look at the angle between the two vectors. Okay? In this case, for example, you could shift vector b upwards so that this situation becomes that this becomes b, and then this is the angle between the two vectors. Alternatively, you can shift A backward so that this becomes the angle between the two vectors. Of course, this angle is exactly the same as that angle because they are vertically opposite. यही तो बताया है क्योंकि mathematicians invented this in the context of they wanted some quantity which gives you the change in this other quantity half mv square. तो जब आप cos phi लोगे तब भी आता है वो change in half mv square. Oh yeah, okay. So you can prove it in general. ये तो मैं particular situation के साथ कह रहा हूँ ना. We will prove it in general. I'll just give you this, the full proof. Okay? ये of course इसका special case है, as you'll see. जब मैं इसी को prove कर दूंगा तो फिर उसको भी prove कर दूंगा. Here, when I prove this, f completely arbitrary होगा, आपका object completely arbitrary होगा, जो path object follow कर रहा हो, that will be completely arbitrary and so on. Everything will be completely general. Here, of course, I'm taking that as a particular example. Okay? Okay. So we have this idea of the scalar product. The scalar product of the force vector and the displacement vector gives you a quantity called the work done. The scalar product is defined like that. From this definition, it immediately follows that this will also be equal to b times a cos phi. If you don't know that, ask your little brother or sister that why is a b equal to ba. He will tell you that 2 times 1 equals 1 times 2. Okay, so anyway, so this is obviously true and this is equal to b dot a. So the order of the scalar product does not matter. Why is this, by the way, also called the scalar product? What do you mean कि direction नहीं है इसका? ये इस number है sure, but what do you mean physically इसका direction नहीं है? Physically, we say that something doesn't have a direction is that when you rotate your coordinate system, that quantity, the numbers that describe that quantity do not change. That's what we mean by scalar. अगर आपके दो vectors हैं, A, B, you set up your coordinate system, one coordinate system like this. That's one coordinate system, the usual horizontal and vertical. So, and then you have another coordinate system which is slightly rotated, for example. ये आपके x prime axis है, ये y prime axis है. In terms of x prime, y prime axis, the components of these vectors are different compared to in terms of the x, y axis. You already saw that when we were doing vectors. Of course, you have all forgotten about that because you want to do machine learning, okay? I lay all fault at machine learning, okay? Anyway, okay, so a scalar, on the other hand, doesn't change. If a scalar has value 20, if you rotate your coordinate axis in your new coordinate system, that quantity is still being described by exactly the same number. That's what we mean by a scalar. So, बताओ, how does that definition lead to कि ये scalar होगा? If I rotate my coordinate system, sure, the components of A and B change. But does the size of A change? Does the size of the arrow B change? Does the angle between these two vectors change? So that's why it's a scalar. If you rotate your coordinate system, this number is not going to change, and that's very powerful. Okay, that means कि अगर किसी चीज ने, किसी reaction ने अगर कोई chemical energy release की है, so अगर मैं उल्टा लटक जाता, I wouldn't have gotten out less energy. I would have gotten out exactly the same energy. Okay. So next time if a bomb is going to go off near you, hanging upside down may not help you, okay? That you'll still be experiencing exactly the same force. Maybe run away, the energy release will be exactly the same except that आप ज़्यादा दूर हो गए, okay? So that's different, okay? ये नहीं है कि scalar नहीं रह जाता, it's still a scalar, but you're in a different coordinate system, okay? Anyway, right? So that's why work done is a scalar. A work done for my simple situation that I'm dealing with is defined like that. What's the limitation of this definition of the work done? Which in turn we know is equal to this thing, at least for the simple example that I am doing. What's the limitation of this definition? F को बारे में मैंने क्या assume किया? It's constant. अभी तक तो मैंने कुछ भी नहीं किया, जो central problem मैंने तय करना. Remember this whole idea of work and energy really comes into its own when you're dealing with the cases where the forces are changing. कई दफा पूछा सर आपको कैसे पता चला इधर न्यूटन सेकंड लॉ नहीं लगाना और वर्क और एनर्जी लगाना है? वेल बिकॉज आई न्यू दैट द फोर्सेस वर चेंजिंग. If you have a problem in which the forces are changing, that's a problem ripe for attack using work and energy. That's the whole idea why work and energy were invented in the first place. Okay, and that's obvious क्योंकि अभी तक आपने जो है in the manner of speaking, very roughly speaking, अभी तक आपने जो सारे न्यूटन साइकिलों के प्रॉब्लम्स अटैक किए, those were essentially linear problems. You were dealing with simultaneous linear equations. इधर आपको पहली दफा एक नॉन लीनियर फंक्शन नजर आया. ओके, एनीवे, ओके, सो नाउ लेट्स गो ऑन एंड जनरलाइज दिस. कि भाई इसको मैंने जनरलाइज करना है टू द केस वेयर द फोर्स इज चेंजिंग. हाउ डू आई डू दैट? इधर जो मैंने लिखा है ये कैपिटल ए और कैपिटल बी, होपफुली इधर अभी भी होगा, लेकिन मैं मिटा दिया. लेट मी राइट इट अगेन. That's where we are going towards. I want to essentially generalize this to the case where the force is not constant. तो फिर मैं क्या करूंगा? The object is नहीं, एवरेज करने की जरूरत नहीं है, इतना फैंसी होती होने की जरूरत नहीं है. The object is going from some point A to another point B along some arbitrary path. So for example, you have some point B over here. आपका ऑब्जेक्ट यूं करता हुआ यूं. I'm just doing that to emphasize that this could be completely arbitrary. So in this case, what do? The force at different points along the path that the object is following is different. You've already attacked this problem before mathematically in a different context. When an object was moving from here to there, from some initial time t is equal to 0 to some time t, and the acceleration kept on changing, how did I find out the final velocity of the object? क्या किया था? What was the basic technique that I used? नहीं अस्तगफिरुल्लाह, पहले काइनेमेटिक्स की तरफ जाओ. Your object is moving with changing acceleration. इंटीग्रल में क्या करते थे? You made slices. You chopped up the time interval into little pieces. You attacked one single time interval, saw what happened over there, and then you added it all up. That's basically what gives you the integral. आप area under curve भी exactly इसी तरह निकालते हो. You chop up your interval into small slices. You essentially make little rectangles, thin rectangles. Find out the area of each thin rectangle. Add it all up. That gives you the area under the curve. But that's one example of this technique. If you have a complicated problem, you chop it up into slices, and if you know what happens when you have a constant force, you will be able to attack this problem even if the force is changing.
Yes, you are correct. It will change in acceleration of constant.
नहीं, कुछ भी नहीं assume कर रहा मैं. Acceleration could be changing in any way whatsoever. If I know how the acceleration is changing, I then integrate it to find out the change in the velocity. वो a of t तो arbitrary है ना. Okay? तो फिर क्या करूंगा मैं इधर? You chop this into little slices. You chop up the path that the object is taking into little slices. And so on and so forth. मेरा हाथ थक गया unfortunately. Imagine that the rest of it has been chopped up. Okay? You need this much imagination to succeed in science and engineering. Okay? For one little segment, if I focus on this little segment, that's my displacement vector. For this little segment. For this little segment, is the force approximately constant or not? Because this segment is so small. Just like when you're calculating the area under a curve, for a little slice, for a little rectangular slice, it's approximately rectangular because the slice is so thin. तो वो little area जो है छोटे से rectangle का, that is f of x times delta x. Because it's so thin, you assume that top जो है वो curve नहीं है, वो straight है. The value of the function for that slice is constant. In exactly the same way, because this slice is so small, I've drawn it slightly magnified for your convenience ताकि आपको नजर आ जाए, but remember it's infinitesimally small eventually. the force is essentially constant. The force for this segment is Fi. And then I say, what's the work done for this segment? You say, well, इस segment के लिए force constant है तो निकाल लेते हैं. I know how to deal with the constant force. You'll have that. So I have the work done for this little segment. Then I find out the work done for this segment, I find out the work done for this segment, and so on and so forth. And then what do? I add them all up. That gives me a quantity called the total work done, or simply the work done, in going from A to B along this path, this wiggly path, okay. So you write that in the limit where this chopping up business becomes more and more and more and more refined, what do I get? The work done then equals integral from A to B of in the limit where delta Si approaches 0, ये क्या बन जाएगा? F dot ds. ये आपका फोर्स जो है, so when you're finding out the area under a curve, let me go back to this. ये आपका A है, ये आपका B है. You chop this up into little slices. For this arbitrary slice that you have over here, आप कहते हो इधर x coordinate basically approximately xi है. It's approximately because of course the slice has a finite width. The value of the function for this slice is f of xi. So the area of this little slice is f of xi delta xi. Total area कैसे निकालोगे? You add it up over all the slices. And then how do you get a more and more accurate answer? You take delta xi approaches 0. And in that limit, that's the definition of your integral. In that limit, this becomes A to B f of x dx. I've done exactly the same thing over there. The only difference is कि दरम्यान में डॉट प्रोडक्ट आ रहा है और ये f और s जो है वो वेक्टर्स हैं. हाँ. किधर इधर? ताकि आपका ज़्यादा एक्यूरेट आंसर आए एरिया का. क्योंकि देखो अगर डेल्टा एक्स ये फाइनाइट है तो फिर ये देखो ये आपने एरिया असल में क्या निकाला है? एरिया असल में आपने ये वाला निकाला है रेक्टेंगल का. ये आपने देखो ये थोड़ा सा एरिया मिस कर लिया. अगर जितना डेल्टा एक्स छोटा होगा, यू विल शो योर कैलकुलस कोर्स, उतना ही एरिया में एरर कम होगा. और फिर ऑफ कोर्स एक डाउट आपके पास हमेशा आएगा क्या कि ठीक है ये वो मैं छोटा कर रहा हूं तो एरर तो कम हो रहा है, लेकिन मैं जितनी टर्म्स ऐड कर रहा हूं वो भी तो इंक्रीज होती जा रही हैं. if there's an error in every term in my sum, maybe the error doesn't go down, because if there's an error of 0.001 in each term in my sum, and if I'm adding 1000 terms, error तो अभी भी 1 का आ गया. If there was an error previously of 0.01 in my each term in my sum, and if I add 100 terms, अभी भी error 1 का है. तो मे बी छोटा error नहीं होता जब आप slices छोटे करते हो. In your calculus course you will show, hopefully, कि जैसे slice कर छोटा करते हो, the error goes down much faster compared to the number of terms. So it actually does help to reduce the error in your total sum. Okay? ये तो बेसिक यार इंटीग्रल की प्रॉपर्टी है, यही प्रूव करना होता है. मेन चीज यही प्रूव करनी होती है when you are dealing with integration. Okay, anyway, but amazingly आपको e raised to power x times sin x को इंटीग्रेट करना आता है, जो मुझे नहीं आता. But anyway, okay, why is that useful? How is that useful? Beats me. Okay, anyway, I mean मुझसे आप पूछो मैं sin x को in terms of x complex exponential लिख के एक लाइन में कर दूंगा इंटीग्रेट. But of course आपने तो इंटीग्रेशन बाय पार्ट्स ही करनी होगी, तो you know. Anyway, right, so coming back to this, the general definition of the work done, this is a natural generalization of this definition. This was the constant force. If my force keeps on changing, this is a natural generalization. Exactly how you generalize the idea of constant acceleration to non-constant acceleration. When you're dealing with non-constant acceleration, you make tiny slices. For each slice, you know how to deal with each individual tiny slice, then add it all up. Okay? The question that remains, however, is क्या जंगल में गुम हो गए हो? Is this once you have generalized this, is this still equal to half mvb square minus half mva square? ये तो आपने कहा है कि भाई ओके ये इसकी नेचुरल जनरलाइजेशन है, but this is no guarantee that this is still equal to the half mvb square minus half mva square. This is fine, yes, but this was only for the case that this is equal to half mvb square minus half mva square for a constant force. Is this still true कि अब ये एक नया मॉन्स्टर जो आपने क्रिएट किया है, is that still equal to delta ke? Okay. The good news for you is कि आधी क्लास इसको देख के जो है उनको बेहोशी के आलम में चली जाती है. In this course, by and large, thankfully for you and thankfully for me as well, by and large, believe it or not, mathematicians और mathematicians तो कम, लेकिन मेरे जैसे लोग इंतहाई दर्जे के सुस्त तेले होते हैं. You might not believe it, but I really hate doing an integrals. ये ज्यादातर इस कोर्स में आपको इंटीग्रल करना ही नहीं पड़ता, because बस भाई, okay, because क्यों? Because it turns out that you can do this integral for different forces and stores your answer. आपका जो पोटेंशियल एनर्जी का आइडिया है वो यही बताता है कि इस इंटीग्रल की वैल्यू क्या होगी. दैट्स बेसिकली व्हाट पोटेंशियल एनर्जी टेल्स यू कि ग्रेविटेशनल फोर्स है, ग्रेविटेशनल फोर्स के लिए इस इंटीग्रल की क्या वैल्यू होगी. दैट्स व्हाट द ग्रेविटेशनल पोटेंशियल एनर्जी टेल्स यू. स्प्रिंग पोटेंशियल एनर्जी टेल्स यू अबाउट कि भाई इलास्टिक फोर्स है तो इस इंटीग्रल की क्या वैल्यू होगी. तो इंस्टेड ऑफ डूइंग दिस इंटीग्रल यू जस्ट यूज पोटेंशियल एनर्जी इंस्टेड. बट ऑफ कोर्स व्हेन यू आर बिल्डिंग अप द थ्योरी यू नीड टू नो कि ये क्या चीज है. Okay, but in practice, don't focus on कि ये आया किधर से है, इसका मतलब क्या है. Don't worry too much about कि ये करना कैसे है, calculate कैसे करना है. Because in practice you will hardly ever need to calculate it. सिर्फ एक केस में, कुछ केसेस में कैलकुलेट करना पड़ता है. So for example, for friction force you actually have to do this integral. But by and large वो बहुत सिंपल होता है कि friction force इस तरफ है, displacement उस डायरेक्शन में है, constant friction force लग रही है, constant force के लिए तो कर ही लोगे ना ये इंटीग्रल. Okay, so वो कोई इतना मुश्किल नहीं होता. Okay, so don't be too worried about actually doing this integral. Again, the basic idea is कि ऑब्जेक्ट आपका ट्रैवल कर रहा है along some path. You have chopped up the path into little pieces. You're calculating essentially f dot s for each little path, and then you are adding it all up. Okay. Okay. Now I have to prove this. देखो खुद ब खुद आ गए हैं सामने. In the most general case, ये एक 3 लाइन प्रूफ है. So A to B, A और B क्या है? A to B of course characterize your initial point and the final point. हाँ. हाँ exactly yes. वो जो डेल्टा S जो है जीरो को अप्रोच कर रहा है. Okay, so F dot ds, this is completely arbitrary. The only F is the net force. So I don't know anything about F क्योंकि मैंने बताया ही नहीं कि फोर्स कौन सी लग रही है ऑब्जेक्ट पे. ग्रेविटेशनल फोर्स, इलास्टिक फोर्स, बेतहाशा फोर्सेस लग सकती है ऑब्जेक्ट पे. न्यूक्लियर फोर्स भी हो सकती है. But I do know now one thing about F, which is नहीं इधर आर्बिट्री कांस्टेंट हो भी सकती है, कांस्टेंट नहीं भी हो सकती. अगर कांस्टेंट है इस केस में फोर्स, तो आपका एफ को क्या होगा? एफ इंटीग्रल से बाहर चला जाएगा. ds के ऊपर इंटीग्रल आपको क्या देगा? द डिस्प्लेसमेंट वेक्टर, टोटल डिस्प्लेसमेंट वेक्टर. sb माइनस sa आ जाएगा ना. sb माइनस sa क्या है? द डिस्प्लेसमेंट फ्रॉम a टू b. तो ये तो वापस वही चीज आ गई. इधर आई नो वन थिंग अबाउट एफ. Astaghfirullah, the total force must be equal to mass times acceleration. Okay, interesting reaction. Okay, that's the first time I've heard that reaction to Newton's second law, but anyway, okay. Okay, hopefully exam को दौरान ये reaction ना आए. Anyway, so ये F is equal to m times, I'll write it as dv by dt dot with ds. Now try doing this derivation without vectors. अब मैं कहा खबरदार करता रहा था वेक्टर सीख लो सीख लो सीख लो सीख लो सीख लो। अब नाउ यू हैव कम एट द पॉइंट इन द कोर्स जहां वेक्टर्स के बगैर गुजारा करना बहुत मुश्किल है एंड बहुत जल्दी और भी ज्यादा मुश्किल होता जाएगा आहिस्ता आहिस्ता। ओके, सो फॉर एग्जांपल एंगुलर मोमेंटम इज डिफाइंड एज अ वेक्टर फॉर एग्जांपल, उसको आप वेक्टर के तौर पे ही समझ सकते हो, वेक्टर के अलावा उसका डायरेक्शन भी आप आराम से नहीं बता सकते, यू हैव टू फिगर इट आउट यूजिंग वेक्टर्स। ओके, एनीवे अब इसके बाद में क्या करूं, ds क्या है, ds is the small displacement vector. So for example in the limit where I chop this path into small pieces, ds is this vector except that it's very small. Can I write that down in terms of dt, the small change in time, the time that the object takes to go from here to here? How is ds related to dt? Yeah, that's the definition of the velocity vector, right? If you know the velocity vector at a particular point, you know the small displacement vector of the object a small time later. आप सारे कंप्यूटर प्रोग्राम से यही इस्तेमाल कर रहे थे ना? Of course आप नहीं कर रहे थे, आप सिर्फ देख रहे थे. Okay. Anyway, so ds equals v dt. So plug this thing in and you get m को बाहर ले जाओ, m is constant as the object moves, the mass of the object is not changing, that's what I'm assuming, dv by dt dot v dt. और इधर of course आपके उंगलियों को खारिश हो जाती है, immediately आप कहते हो I know what to do, dt cancels this dt and then you are ending up with dv dot v. In a manner of speaking, that's fine. That's not mathematically disallowed. That's fine if you interpreted that as कि भाई ये infinitesimals का ratio लिया और फिर एक infinitesimal से उसी infinitesimal से multiply करके you're taking a sum. Except that then you get immediately stuck. Because to make further progress, you need to know the relative directions of v and dv. dv is the direction of the change in the velocity vector, aka the direction of the acceleration vector. V of course gives you the direction of the velocity vector. This is a completely general situation. आपको नहीं पता उनके directions के दरमियान क्या relationship है. They could be parallel. So if you are pushing a box horizontally, the velocity of the box is parallel to your force vector, is parallel to the acceleration vector, is parallel to the dv vector. If a particle is moving in a circle uniformly, the acceleration or dv is pointing towards the center. The velocity of the particle is tangential. In this case, the two vectors are perpendicular. जिसका क्या मतलब है कि v dot dv क्या होगा? Zero, which means कि उसकी change in kinetic energy क्या होगी? Zero. That's another way, yet another way of seeing a particle in uniform circular motion. The speed does not change, लेकिन of course आपने फिर भी v square is equal to u square plus 2as लगा देते हो उस पे. Acceleration अल्लाह जाने कैसे निकाल लेते हो उसकी. Okay. Anyway. क्या चीज? If v dot dv for circular motion, say you looking at this point, ये आपका v का डायरेक्शन है, dv का क्या डायरेक्शन है? dv is the same direction as acceleration. देखो acceleration equals dv by dt. Or in other words, dv equals a times dt. ये आप प्रोग्राम से यही इस्तेमाल करते रहे हो, एक्सेप्ट कि आपने कभी इस्तेमाल नहीं किया अभी तक. But anyway, okay. The direction of dv is exactly the same as the direction of the acceleration. So the acceleration, you know, for uniform circular motion, the acceleration is pointing towards the center. The velocity vector is tangential. This is the direction of dv. So v dot dv क्या होगा? Zero, because the angle between them is 90 degrees and the cosine of 90 degrees is 0. Uniform circular motion के लिए. Yes, of course. मैं एक एग्जांपल करा रहा हूँ. वही मैं कह रहा हूँ कि अगर आप ये काम कर दो आप फंस जाते हो, बिकॉज आपको नहीं पता कि किस सिचुएशन के साथ आप डील कर रहे हो. अगर आप एक डब्बे को पुश कर रहे हो, इन दैट केस v and dv आर पैरेलल. अगर नॉन यूनिफॉर्म सर्कुलर मोशन है फिर क्या होगा? इफ दिस ऑब्जेक्ट इज स्पीडिंग अप, फिर आपको इमीडिएटली उसी वक्त पता चल जाता है भाई एक्सेलेरेशन वेक्टर परपेंडिकुलर नहीं हो सकता वेलोसिटी के, बिकॉज इफ द एक्सेलेरेशन वेक्टर वाज परपेंडिकुलर टू द वेलोसिटी वेक्टर, फिर उसकी काइनेटिक एनर्जी कैसे इंक्रीज हो रही है? तो फिर एक्सेलेरेशन वेक्टर का क्या डायरेक्शन होगा? तो slanted होगा. That would be done with the direction of dv. You would have a tangential component of the acceleration, you would have a radial component of the acceleration. The radial component of the acceleration is responsible for changing the direction of the velocity vector. The tangential component is responsible for speeding up the object. Depends, अगर आपने इसको कंस्ट्रेन कर दिया कि सर्कल में मूव करे, वो तो आप कह रहे हो कि प्लेन में मूव कर रहा है. अगर मैं एक ट्यूब बना दिया फिर तो उसी में मूव करता रहेगा ना. वो फिर फ्रिक्शन को भी एनालाइज करना पड़ता है कि किस तरह मूव करता है. ओके, सो टू मेक फर्दर प्रोग्रेस, द पॉइंट बीइंग डोंट डू दैट. Why am I highlighting this? क्योंकि this is one of my pet questions to give in the midterm. Prove the work-kinetic energy theorem. जो कि इस दफा नहीं दूंगा मैं obviously, क्योंकि मैं बता चुका हूँ. Okay, anyway, the point being that derivations are important. Why are derivations important in this course? Because that's the first of all the foundation of the theory, and more importantly, अगर आपको जब डेरिवेशन समझ आती हैं तब आपको समझ आते हैं कि फलानी इक्वेशंस की डेरिवेशन के पीछे assumptions क्या हैं. अगर जब तक वो नहीं आप समझोगे, you will end up applying many equations in situation in which they cannot be applied in the first place. आप जब डिराइव करते हो v स्क्वायर इज इक्वल टू u स्क्वायर प्लस 2as, अगर सिर्फ ब्लाइंडली याद कर लो, आप ये नहीं याद करोगे that this is only applicable for the case where the acceleration is constant. और फिर आप स्प्रिंग वाला ऑसिलेटिंग स्प्रिंग वाला प्रॉब्लम आप कर रहे हो कि v स्क्वायर इज इक्वल टू u स्क्वायर प्लस 2as के साथ. Okay, so that's more importantly, that's why derivations are important. You really get to understand. आप nuts and bolts को देखते हो, okay, डिटेल में जाके अंदर से जाके देखते हो कि क्या हो रहा है, rather than the ऊपर वाले cursory से point of view. Okay, you literally get your hands dirty. Okay, anyway, the idea then is this. Rewrite this thing in the square brackets. I literally did nothing except put square brackets. Rewrite this thing in the square brackets in another way. Once upon a time, 1.5 months ago, I asked you to do something, which was there was some question in the recitation, I think, or somewhere in the readings as well, that was to do with the properties of the dot product. तो डॉट प्रोडक्ट असल में आप बहुत पहले देख चुके थे, एक्सेप्ट कि आज आप ऐसे मुझे शक्लें बना के दे रहे हो जैसे पहली दफा देख रहे हो. But anyway, if you have two vectors that depend on time, okay, so A is a vector that keeps on changing with time, B is another vector that keeps on changing with time, and I'm looking at the rate of change of this dot product. Vector A keeps on changing with time, vector B keeps on changing with time, so obviously the dot product in general should be changing with time, and then I can talk about what's the rate of change of this dot product or the scalar product. It turns out, and that's the proof I asked you to do, is that this is equal to dA by dt dot B plus A को constant रखो, B को differentiate करो. So exactly the same product rule, exactly the same analogous product rule applies when you're looking at the dot product. एक को constant रखो, दूसरे को differentiate करो, फिर उल्टा कर दो. Okay, I'm going to use that without giving the proof. The proof is there as a guided question in the readings. वो chapter 1 में है, chapter 2 में, I forget what. Okay, but anyway, so let's use that proof. ये proof मैं कैसे इस्तेमाल करूँगा? ये वाला proof इधर मैं कैसे इस्तेमाल करूँगा? नहीं dt को बाहर नहीं देना. देखो, if I have something like this and I say A से B integrate करो, what's the answer? Astaghfirullah. F of B minus F of A. To integrate df by dx is trivial because you already know the antiderivative of df by dx. The antiderivative of df by dx by definition is f. Or in other words, dx कट जाता है. You are adding up small changes in the function to get the total change in the function, and that's fine. तो आइडिया इज सिंपली इज कि अगर ये देखो dt जो डेरिवेटिव है वो सिर्फ इसके साथ चिपका हुआ है. अगर मैं डेरिवेटिव किसी तरह ये सारी चीज के साथ चिपका दूं, आई वुड बी डन. फिर मैंने वही काम करना है. कैन आई पुल दिस डेरिवेटिव आउटसाइड, इन अदर वर्ड्स, नॉट आउटसाइड द इंटीग्रल बट आउटसाइड द स्क्वायर ब्रैकेट. Okay, that's the idea. And then it's obvious कि इसके बाद क्या करना है. If I look at d by dt of v dot v, ये किसके बराबर है? Using the product rule, this is equal to dv by dt dot v plus v dot dv by dt. Or in other words, this is equal to a dot v plus v dot a. But the order in the dot product doesn't matter. So this thing is equal to 2 dv by dt dot v. अब पहचाना है ये I need to simultaneously be an eye doctor as well. ये जो चीज है in the pink box कहीं और नजर आ रही है आपको? अस्तगफिरुल्लाह, वो स्क्वायर ब्रैकेट में क्या चीज है? ये देखो, that's exactly the same thing as the thing in the pink box. And therefore this thing in that underlined pink thing equals half of the derivative of v dot v. ये 2 को मैं दूसरी साइड पे ले गया because I just need the thing in the pink box. I don't need the whole thing. Okay, so this thing equals, in other words, ये half आ जाएगा. So this is m a to b half of d by dt v dot v dt. This half, of course, I can pull outside the integral. That's just a constant. तो ये और फिर ये क्या? अब आपके मुंह में पानी बाहर आना चाहिए. dt कट गया, so you're adding up small changes in v dot v or adding up small changes in v square. V dot v, remember, is just equal to the magnitude of v, which is the speed, multiplied by magnitude of v, which is also the speed, times cosine of 0, because the angle between these two vectors is 0. ये एक ही vector है. So you just get v square from here. Okay, and बाकी half m है आपका. और limits डालोगे तो क्या आएगा? Half m vb square minus half m va square. That's exactly what you have. So the integral of the force over distance, roughly speaking, now I made it precise कि आपने force vector को dot product लेना है छोटे से displacement vector के साथ, उसको add up करना है. That's what I mean, the integral of the force over distance. That equals half m v square minus half m v square, और फिर आप 0 लिख दोगे. Half m vb square minus half m v, as in the final kinetic energy minus the initial kinetic energy. You define the quantity half m v square as the kinetic energy. Okay, right? Let's do one example. Let's use this to attack the problem that I posed. ये आपकी अर्थ है, बहुत दूर से हाइट h से आप एक ऑब्जेक्ट रिलीज कर रहे हो from rest. From height h, you are releasing an object from rest. The first thing that you do over here is, when you want to find out the speed of the object when it hits the surface of the earth, the first thing that you should do is draw the free body diagram. That is still true. Okay, अगर free body diagram से आपके जान नहीं छोड़नी जब तक ये कोर्स जिंदा है. Okay, so you have this object, it falls like that. So in this case आपको पता है trajectory क्या है ऑब्जेक्ट की, it just falls towards the surface in a straight line. Many cases this question is very tricky, क्योंकि आपको कई केसेस में trajectory ऑब्जेक्ट की पता ही नहीं होती कि क्या पाथ क्या फॉलो कर रहा है वो. Then it seems कि वो आप इंटीग्रल नहीं कर सकते क्योंकि ds का ही नहीं पता. Okay, in this case it's clear. Okay, so anyway, so what you have over here is कि ये center है, and then you set up your axis. ये मेरी y axis. At this arbitrary point, this is y. The y is some arbitrary position of the object as it's falling down towards the surface of the earth. What's the force at this point? Remember, मैंने ऊपर की तरफ लिया तो Ey is like that. तो force को as a vector मैं कैसे लिखूंगा? Force नीचे की तरफ है, of magnitude. अस्तगफिरुल्लाह, कोई मुश्किल मैंने ये नहीं पूछा कि क्या हो गया है, किसने जुल्म किया आपके साथ मुझसे पहले. ओके, क्या हो गया, क्या नींद नहीं आई, क्या हो गया? ओके, minus gmm over y square ey. That's the gravitational force that this object is experiencing. आपका डिस्प्लेसमेंट वेक्टर क्या है? डिस्प्लेसमेंट वेक्टर क्या है इस केस में? नहीं, वो तो टोटल डिस्प्लेसमेंट वेक्टर है. स्मॉल डिस्प्लेसमेंट वेक्टर किसके बराबर होगा? जब एक ऑब्जेक्ट यहां से यहां जा रहा है, उसकी क्या, कौन सा कोऑर्डिनेट चेंज हो रहा है? y. So you get dy ey. इधर ऑफ कोर्स आधी क्लास जो है वो ज्यादा जो है ना, जिसको कहते हैं ओवर क्लाइवर होना, वो ओवर क्लाइवर हो गए, कहते हैं भाई डिस्प्लेसमेंट वेक्टर नीचे की तरफ हो जाती है, तो इसलिए दिस इज माइनस dy ey. Why should you write plus dy ey and not minus dy ey? पॉइंट नीचे की तरफ ही आ रहा है. नहीं, वेक्टर ही है, डिस्प्लेसमेंट वेक्टर है यार, छोटा सा डिस्प्लेसमेंट वेक्टर है. एग्जैक्टली, dy itself is negative. वो साइन ऑलरेडी dy के अंदर मौजूद है. As the object is moving downwards, dy is negative. The value of y is decreasing as the object moves downwards. The change in y is negative because the value of y is decreasing. तो यही आपका आएगा. And then you have f dot ds किसके बराबर है? This equals minus gmm over y square dy. And then इसके बाद वर्क डन निकालने के लिए क्या करना है? As the object moves from here, from height h to the surface of the earth with the radius of the, where the value of y is the radius of the earth. Yes, okay. तो आपने अब इंटीग्रेट करना है ना, और ये तो आपको ऑफ कोर्स कहीं ज्यादा बेहतर आता है मुझसे. So you have minus gmm over y square dy. This is the work done on the object, because the only force acting on the object is the gravitational force. This is the total work done. You have to integrate it from point A. Point A पे y की वैल्यू क्या है? नहीं, ऊपर करके re plus h, और इधर क्या है? और फिर क्या आएगी? ये आंसर क्या आएगा फिर इस इंटीग्रल का? Again, setting up the integral is the more difficult part. Now it's straightforward. 1 over y square का एंटी डेरिवेटिव क्या होता है? 1 over y square का minus 1 over y. Minus minus कट जाएगा. You'll just be left with 1 over y, so you'll be left with gmm 1 over y. इसके अंदर लिमिट्स डालो आपकी re plus h, and you put in re, and you get from here, you get basically gmm 1 over re minus 1 over re plus h. Physically speaking, should this answer be positive or negative? Positive work done corresponds to an increase in kinetic energy. Negative work done, yes, obviously अगर मैं कह दिया तो it's one of the two, right? That was a nice thing with this question, okay? Binary choice. When the work done is positive, the kinetic energy increases. When the work done is negative, the kinetic energy decreases. As the object comes down, it's speeding up. तो kinetic energy increase हो रही है, decrease हो रही है. तो work done क्या होना चाहिए? Positive. ये देख लो, re छोटा नंबर है यार, re plus h से. The denominator, this denominator is smaller than this denominator. This will be a bigger number compared to this. तो आपके पास एक positive number ही आएगा ना. And this equals half mv square, where vb is the speed of the object at the surface of the earth. Solve for vb. Okay? ठीक है? हाँ, ये मेरा ऑब्जेक्ट यहां से यहां गया है. दिस इज ds, ए स्मॉल डिस्प्लेसमेंट वेक्टर. हाँ, वो जो मैंने प्रूव किया था कि टोटल वर्क डन इक्वल्स द चेंज इन काइनेटिक एनर्जी. मैं इनिशियली मैंने रेस्ट से छोड़ा है ना, इसलिए VA 0 है. अगर VA नहीं 0 है, इसको इंक्लूड कर. नॉट